Hi, hello everyone. Good morning and good evening to whichever part of the world you are in. A very warm welcome to each one of you for today's expert live session. Morning and good evening to whichever part of the world you are in. A very warm. I'm Chanukya, founder of DeFi, and if you're able to see and hear me, please feel free to drop a hi, hello from wherever you are on YouTube or on LinkedIn. We'll be happy to see your hellos, big hellos. And I believe most of you know about DeFi. But for those unattended, here's a quick introduction about DeFi community. We are a global AI community with a purpose to educate and build AI for all to solve meaningful problems. On one hand, the community is addressing the problem of AI education by providing free courses from experts. And on the other hand, through our community initiatives, we are solving real world problems such as earthquake prediction, safeguarding NFTs, etc., with the help of the community. And today's session on gradient boosted decision trees is one such initiative to democratize data science education. And our heartfelt gratitude and many thanks to Mr. Ben for kindly agreeing to do this session. And with that, let me introduce the speaker for today's session. Ben is the vice president and head of data science at Dekeo. Before his stint at Dekeo, he was a data science manager at Expedia. He has built scalable systems that cater to billions of requests. And with that, let me add him to the stream. Hi, Ben. Thanks for joining in, and we are looking forward to learning from you today.
Yeah.
And yeah, I mean, it's all yours, and I'll you can take it forward from here. Yeah, thanks for joining in.
Well,
Yeah.
thank you. No, I'm certainly excited to be a part of it, and I really the education aspect of data science is important to me, and I really think that that your organization is doing a great thing, and I'm certainly excited to be a part of it. You'll get to know me. I'm a bit of a talker. I love to talk about stuff that I find really interesting, and this is one of the things for me that has always been it has always been kind of the first arrow in my quiver as a data scientist. And just to ask, you can see my screen? Am I sharing correctly?
Yes. Yeah, we are
Okay.
able to see, and we can already see people addressing it. Yeah, you can go ahead.
Awesome. Okay, cool. So I have the link for this on Google Docs, and make sure that that's passed around after this. But no, I really enjoy I love math. I mean, it's like one of the things that I've been one of the few things I've been good at in my life. I really enjoy math, and I really enjoy talking about it. And this is a subject for me, which is especially if you're early in your career as a data scientist. I think gradient boosted decision trees are a good tool to pick up early in your career. So a little bit more about me. My family and I recently moved to Raleigh, North Carolina. If you're in Raleigh, happen to be in Raleigh, let me know and let's go grab a coffee or a beer. I'm the VP, head of data at JiffyShirts.com. Jiffy Shirts is a company owned by Dekeo. So Jiffy Shirts, we are the leading e-commerce vendor of blank apparel. For example, the shirt that I'm wearing, if you go to a conference and you get a shirt from a conference, it's not necessarily, we don't print on the shirts, but we sell the shirt that kind of sits underneath the logo. Our customers tend to be crafters, people who own small businesses, Shopify shops, Etsy shops, etc. Before this, I was working at Verbo, so as mentioned, I own the core search algorithms there, and those search algorithms serve up to 10 million requests a day. $8 billion in e-commerce kind of went through our front door. And then before that, RetailMeNot, a couple of other Austin area startups. I get asked a lot, how do I get into data science? Or, do you have tips for early career data professionals? I'm old enough, so I got into the field kind of by calling myself a data scientist and sending resumes around. I don't think I could do the same thing today, so I would say all of my advice, except about gradient boosted decision trees, all of my advice I would say take with a bit of grain of salt, because I got into data science and I started in data science in a very different time. The last thing, please find me on LinkedIn. If you folks have questions on anything that I say here, love to answer them. I'd love to connect with you on LinkedIn. If there's any way I can help, please let me know. We don't have any positions at Jiffy right now, but certainly when those positions come up, I'll post them on my on LinkedIn. So when I was thinking about how to put together this talk, I kind of wanted to give y'all I kind of wanted to structure it sort of, if I was a data scientist maybe earlier in my career, what does my day-to-day life probably look like? So 80% of the time, I would say that this is true. If you're working in, if you go to Tesla and you're working on computer vision, if you go to, if you're working in core Google search algorithm, if you go to, if you go to a company, like there's a company in Raleigh called LexisNexis that does legal document search, like legal information retrieval for legal, for lawyers. If you go to one of those places, those are the 20% cases. You're probably, your life doesn't necessarily look like this, but I think for a large number of the data science jobs that you're likely to have in your career, a lot of the day-to-day is probably going to look like this, right? You have stakeholders who really want to understand how your model works. You have to be able to explain how the model is working, and your stakeholders tend to be people who are more senior in the organization. They got there by being skeptical, and they're not going to defer to you just because you're better at math than they are. They're going to demand from you that you understand how the model is working, that you can explain it to them. You're always, again, outside of like images and text, you're almost always going to be presented with tabular data. And if life is never fair, and that tabular data is going to come with lots of holes, right? There's going to be lots of stuff missing from it. In addition to that, again, stakeholders have opinions about the relationship, what relationships should look like, right? There's business logic that has to be incorporated into a prediction, right? If you know in your business, if there's a particular relationship that is well tested, that everyone understands, and your model discovers a different relationship, you have to be really, really careful and really understand, is that a spurious relationship that the model discovered, or is it contradicting kind of the conventional wisdom? And if it's a spurious relationship, it doesn't matter how good your F1 score is. It doesn't matter how good your model performance metrics are. If your model is telling a stakeholder something that doesn't make sense to them, likely what's going to happen is they'll reject all of your conclusions until you can explain why the thing that doesn't make sense to them either is wrong or, is different than what they had understood. So you really have to be careful about that stuff. I've been in very contentious meetings between data scientists and C-suite where the data scientist didn't understand what the executive was saying. The executive didn't understand what the data scientist was saying, and very uncomfortable situation with people just talking past each other. And it's because of this, because the relationships that came out of the model weren't sort of common sense relationships. And then finally, the last thing, and I would say that this is stakeholders. So this isn't just a work thing. This is probably going to soon be a regulation thing. Stakeholders care about how your model is making decisions, especially if you're in, places with we're making decisions about employment. You're making decisions that really affect people's lives. You really have to be able to explain how those decisions are being made, and that's a fact of life now. It's a convenient thing to be able to explain the predictions now. But I think it's going to become a legal thing in the next couple of years to be able to explain your prediction for some, if not most, models. And what I want to convince you of in this talk is that gradient boosted decision trees sort of solve all of these problems for you. If all of the sort of day-to-day challenges that you get as a data scientist, in 80-90% of the cases, gradient boosted decision trees will make your life easier. And that's kind of how I want to frame the talk today. So first, gradient boosted decision tree models are, I have to qualify this one, they're relatively easy to understand. I think outside of linear regression, they're really, really easy to understand, kind of depending on how you use them. So let's talk about that a little bit. So this code took me 1 hour and 2 minutes to write last night. It took me an hour to fix my Conda environment. And it took me basically a minute and a half to remember how to do the second line with NumPy array operations. So very simple, quick to value. If you see what I'm doing here, in the first line, I'm generating just 500 data points. They're a random number between 0 and 1, right? So I have a single feature in the matrix. For the indicator, basically what I'm doing is if the feature is greater than a half, I'll assign it 1. And if the feature is less than a half, I'll assign it 0. So this is what the flatten and round does. So now I can run this very simple data set through my classifier. So this is light GBM. Very simple again, single tree, single split. And then let's take a look at the tree. And you can see, okay, the model does a pretty good job of discovering the decision boundary at 0.5, right? If the column 0, if the number is less than 0.5, it adds negative value to the model score. If it's greater than 0.5, it adds positive value to the model score. And so this is how it's discovering the two classes. Leave 0 points the overall prediction towards 0, the class 0, and leaf 1 points the prediction towards class 1. So everything's working here just like it should. Discover the relationship like it should. But really, this is what the sort of most fundamental kernel of all of these algorithms are. You can get really, really fancy with them and do splits, and we'll talk about bagging and boosting in just a second. But at the end of the day, it really comes down to a single split at a single node, right? And this is really how the model works. And it just does this over and over again. So how do we get more complicated predictions, right? You can see that this is a single feature. This is a very easy decision boundary. How do we get more complicated? How can we model more complicated relationships? And so there's 2 different ways. This is a great interview question, by the way. I like asking this interview question. Is the difference between bagging and boosting, right? And the way that I think about this, and this sounds a little goofy, but it really does help to explain it sometimes. I think about democracy. We have a model democracy, or we have sort of turtles all the way down, right? And so it's bagging versus boosting. Bagging for me is model democracy. You put a bunch of models together, you call an ensemble of models together, and you let them vote on a prediction. You may want to weight the vote by, how certain a model is about its prediction. You may want to, you don't have to use the same type of model. You can build an ensemble of all types of different models and let them vote. But essentially what you're doing is you're just putting a bunch of models together that are pretty simple. And you're relying on the law of large numbers. You're relying on sort of all of the error terms from all these models canceling each other out, right? So you pick a simple model. That simple model has an error term that's distributed like a normal number. It's like a normal distribution about 0. And if you get enough of those models together, all of this random error terms that are all distributed in a normal distribution about 0 should tend to cancel each other out. And so this is kind of what's going on under the covers. Another good analogy here is like your investment portfolio. If you own a single stock, you're exposed to really wide swings in returns. You can get a very high return or you can get a very low return. But if you own a bunch of stocks, all of the volatilities of those individual stocks kind of cancel each other out. And so that's why in your retirement fund, you probably own a lot of index funds, right? You buy every stock in the stock market, and then you're just relying on the stock market generally going up. You don't care about how one stock performs. All the variance cancels it out, and you get just sort of a steady, slow growth portfolio. Another advantage, aside from being easy to explain and something that stakeholders really understand, it's harder to overfit these models. Each model itself is relatively simple. And so it's hard to get into a regime where you're doing a lot of overfitting. Challenges, though, it could be harder to model some more complex interactions. You're not getting a lot of feature interaction depending on the complexity of the individual models in the ensemble. And you have to, and you may, the variance of an individual estimator may be actually quite high. And so you may need to have a lot of trees in your forest before you get a low enough variance. So that's bagging, basic idea behind bagging. Boosting so boosting is sort of the more common approach, I think. The ensemble approach, both of these have won tons of Kaggle competitions, so like well vetted. But so the boosting approach is essentially you build a model F1. So you have some indicator Y, you have some features X, you build some model F1, and that model comes with an error term. So instead of building a bunch of models and relying on averaging to cancel all of these error terms out, now we want to explicitly model the error term as a function of the features that we have, right? So we take the error term from the first model and we try to model it. We try to build another model on top of it, and that leaves us with another error term, epsilon2. And so you can play this game again. Now we take epsilon2 and we build another model, F3, and that leaves us with another error term, epsilon3. And so you continue this process until you get until you're, lots of ways to stop it, but you can continue this process until epsilon gets small enough based on some validation set. You can cut off this process in a explicit way, say like I want 100 estimators, so I want to do this process 100 times. Lots of ways to regularize it in that sense. But this is, this is why I think it's a tree on top of a tree on top of a tree, right? There's a I don't know, a metaphysical theory that the world exists kind of on the back of a turtle, and you like scratch your head and say, well, what about that turtle? Where does that turtle live? And like, well, that turtle lives on top of another turtle, and so there's sort of turtles all the way down, and we live on the back of this this giant turtle who's taking us through the cosmic the cosmic universe. And so this is what I think about, like, turtles all the way down. These models are great because you can model more complex interactions, right? You can and you can, because you're explicitly modeling the variance, you're explicitly trying to explain the variance at each step. You can result in an estimator that has very, very low estimate. You can result in an estimator that has very, very low variance. But that also means that you can overfit with these models. You can really overfit, and if you have a little bit of a bias in your data set, even though you get the typical things that happen when you overfit like that. The other thing too is, you notice I've used a lot more words explaining this approach than the bagging approach, right? So it's a little bit harder to explain this approach. And if you're rolling your eyes a little bit at me calling this a pro or a con, like it is something that is going to make your life difficult as a data scientist. And so, like, how can you avert the things that make your life difficult as a data scientist? Well, you can use a model that is easier to explain to your stakeholders. And so I think that's a power of, like, the gradient boosted trees. Generally, the tree bagging models are even maybe a little bit easier to understand. So more information on this stuff. Elements of Statistical Learning by Tibor Shani. It is a hard book to read, but it is it should have lots of pencil marks and dings and dents on it. Your copy should. It's still the best book, I think, for understanding these things at, like, the most fundamental levels. I will say, though, that the XGBoost documentation on decision trees is fantastic. I would absolutely recommend going to the XGBoost documentation and just reading through that and really understanding, really focusing, really understanding those simple examples in the XGBoost documentation, because it's very, very well written. Okay, so gradient boosted decision trees, easy to explain, like, how the model works to stakeholders. The other thing that is nice about gradient boosted decision trees, they win on tabular data, right? Your life as a data scientist is probably going to be rolling around in all kinds of different tabular data. Gradient boosted decision trees, if you don't know anything about the space, if you don't know anything, about the thing you're trying to model, if you the gradient, and if you have tabular data and you have a classification or regression problem, gradient boosted decision trees should be the first kind of arrow out of your quiver. So this is a paper from 2021. You can read it if you like, but just knowing the results are good enough. So what they did in this paper was they took a bunch of, I would call fancy or sophisticated neural net models. So they took some neural net models that had been specifically built and tuned to operate on tabular data. Okay. So you have, so there's, I think, 5 or 6 different models, papers people published that said, here's my crazy PyTorch architecture, and I'm going to throw this at some tabular data. And they showed in the papers that the model architectures that they built had good performance compared to alternatives. Okay. So in this paper, what they did was they took those models, they took the publications, they took the data sets that those models used in those publications, and then they just threw XGBoost at it. And so they compared, here's your fancy neural net model, here's the data set that you used, and here's XGBoost with no feature engineering, with minimal hyperparameter tuning, and we're going to throw that at the problem and see how it does. Okay. So here's the results. Again, there's a lot to digest here. The rows in this chart, in each of these charts, are different models, right? So the top row is so we have XGBoost, and then we have these 4 different neural net models that were built. So in addition to these 5 models that were tested, they looked at some ensemble approaches. There was just a simple ensemble. There was a And this is just kind of averaging together the four models, the four neural net models. There was a deep ensemble, which was a little bit more sophisticated way to combine the four models. And then there was a deep ensemble with XGBoost. So you consider, we talked about ensemble approaches, the bagging approach just a couple slides ago. This is the same thing. We have a bunch of deep models. And oh, by the way, let's just throw XGBoost in there because it's so easy to use. Okay, so those are the different models that we tested. The columns, you look, each of these columns are different data sets, right? So I don't know all these data sets. I know the Higgs data set. I've heard of MSLR before. These are all different data sets kind of in the columns. And then below the charts, you can see these brackets, and this says TabNet. So these three data sets, the first three data sets were the data sets that were used in the TabNet paper. All right, so unsurprisingly, TabNet does really well on these three data sets that they published with. Right, but then you can see that there's some other modeling approaches that do similarly well, you know, these sort of tabular neural nets. But what I want to call attention to is if you compare each of these data sets and you compare each of these model results with XGBoost, what you find is that XGBoost is really not that bad. It really is pretty good. It pretty is middle of the pack, even when comparing to much more sophisticated modeling approaches. The other thing that's really interesting is that you can see this deep ensemble. The results of the deep ensemble are almost always improved by including XGBoost. Almost always improved by including XGBoost, no matter the data set. But I think for me that the real interesting thing is if you compare XGBoost to the model that actually won each of these data sets, you find the difference really isn't that far away. And to me, that's a really interesting result. XGBoost is rarely the best model in terms of these relative performance metrics. But remember, there is very little hyperparameter tuning here. There isn't a whole lot of feature engineering. And the feature engineering for me in my career has been, you know, to me, that's how you make your money as a data scientist. Like you can, you know, scikit-learn, import model, model.fit, like, yeah, okay, you can type, that's awesome. But the feature engineering is really where you make your money as a data scientist. And so if I feel confident that with a little bit of feature engineering with these models, you could really improve the performance of XGBoost and put it even closer to some of the winners in each of these on each of these data sets. In most cases, XGBoost performs at least as well as or at least close to as well as the model that on the data as the model in the publication did. And so, you know, you can go and do a bunch of work building out your PyTorch architecture and making sure that your data is right and you have the data transformations where you want them, or you can just import XGBoost and throw XGBoost at the problem. And to me, that's a really valuable thing. The XGBoost beats the performance of the original model on the data set that was used in publication. And then in almost every case, I think I pointed this out already, almost every case the deep ensemble performance is improved by inclusion of XGBoost. I apologize, I didn't say this at the beginning. These numbers are all, I think, mean squared errors. There's some relative performance metric on the model that makes sense for the particular problem. And I think some of them are not mean squared errors. I can't remember exactly what they are, but essentially these are, you know, the lowest number in each of these columns is the best one. All right. Okay, good. So
Ben,
yes, go ahead.
Yeah, Ben. I think we have a couple of questions. Do you want to pick it now, or should we take it at the end? What do you prefer?
I'm happy either way.
Yeah, so there are a couple of questions. Maybe someone is asking, is deep ensemble same as stacking? And and then one is a little a different question where Tan has mentioned that it was put intuitively the analogy of democracy versus turtles, and how important is it to understand the math part of it when we start as a beginner? It'll be great if Ben can share his journey on how he learned.
Oh yeah, absolutely. Yeah. So let's talk. Yeah. So how to answer these questions. So number one, so the second question is how much do you have to understand the math? The first question is ensembling the same as stacking? I think stacking is something slightly different. I think, and I've not kept up with the literature. To me, it's you're You're just throwing a bunch of models in a bag, and you're kind of figuring out how to aggregate those together. I think stacking versus ensembling user in bagging versus stacking. I think in bagging it's the same model, and stacking isn't the same model, or there's some distinction like that. But I don't I'm not super familiar with the terminology stacking. In terms of understanding the math behind these approaches, there's definitely you definitely should spend some time understanding the math. I think what's more important is that you intuitively understand how things work. So my background is in physics. I did a PhD in physics. There, in graduate school, there were two types of people. There were people who were very, very good. There's people who are very, very good at calculating things, and there are people who are very good at understanding things. And you can really go down the route of really, really understanding the math and getting really good and going through a lot of pencils and a lot of paper and getting really good at calculation. Or, your style, your mind may naturally work to understand the concepts at a high level. And then as you sort of fill out that understanding, as you go deeper and deeper, understanding it in kind of an intuitive way, in sort of a mechanical way, then you start to fit the math to it. I'm very much the second type. I'm not very good at calculations, right? I did a PhD in physics. I did a lot of calculations. It was because I had to. It's like I eat vegetables. I don't like to eat vegetables, right? But I eat vegetables because supposedly it'll make me live longer or something. But it's not something that it wasn't the way that my mind naturally works, but it was something that it was like, you have to eat your vegetables, otherwise you're never gonna see your kids graduate college. So to me, at some level you have to engage with the math. It doesn't have to be the first thing that you engage with. And if you're a more intuitive thinker, and as I am, and that's why a lot of these dumb analogies like democracy and turtles, a lot of those really simple examples are the ones that'll teach you the most. I think there's a quote by Wolfram, who wrote Mathematica. If you don't know Stephen Wolfram, he's an interesting guy, but who says something like don't underestimate the power of a very simple example, right? Einstein said I make things as simple as possible, but no simpler. You get things down to the very simple, and then you can understand kind of the very fundamental mechanics. To me, at the end of the day, the tree is it's a node and it splits, and there's some way to make it split, and you can go and figure out and calculate the math. How does it know what feature to pick to split on? You can go and figure that out to calculate the math. But at the end of the day, the math is going to give you a little bit of context to the overall overarching concept. As you go deeper into the field, as you get past trees, you probably have to understand more of the math of neural nets. If you want to do, if you want to build a neural net, I would encourage you to go work out the back propagation equations. And it sucks, but everybody should do it once, because that way you'll really understand. You'll struggle with oh, well, this index of the matrix, when I do this matrix multiplication, how do I differentiate a matrix? You have to struggle with those things so that you understand them. And so I think, there's definitely modeling approaches where you don't have to engage with the math as much, and engaging with the math will give you a little bit more context, and you should do that throughout your career. There's other approaches that are inherently more technical, that are inherently more mathematical, and you'll have to engage with the math sooner with those. I hope that's a reasonable answer. I think I felt like I gave a yes and no answer, which I always kind of hate. But
I think that's great. I think there is yes and no. I mean, it's always good to get that motivation by understanding the intuition part of it, and then gradually you'll have enough motivation to get into the math and the complex side of it once you understand the intuition. So it's a practical way. I think it's important you don't overwhelm right at the beginning. Better understand the intuition, and then you'll have enough motivation to understand what magic is going around at the back end.
Yeah. The overarching theme is stay curious. Stay curious. You got to stay curious.
Thanks.
So cool. Yeah, absolutely. Okay, so gradient boosted decision trees do great on tabular data. Gradient boosted decision trees are easy to explain. Gradient boosted decision trees handle missing data elegantly. The heuristic that LGBM uses, and I think this is similar across all the packages, all the gradient boosted decision tree packages, but the heuristic for LGBM is to allocate the nulls to the side of the split that reduces the overall loss function the most. You got to think about that one a little bit, but essentially what you're saying is, I have this split that's happening. I don't know whether I should go left or right here. Let's wait until the end of the iteration, and then let's check if I went right, what would my loss function be? And if I went left, what would my loss function be? And then pick the direction of the split that reduces the overall loss function the most. The categoricals are handled slightly differently, but essentially it's like it's a loss function argument. To me, a little bit of a story here. When I was at Expedia, we worked for a long time to build a neural net for our ranking model. We worked for a long time to build a neural net for our ranking model. We eventually got it. It eventually won. I left at about the time that test was wrapping up, so I'm not sure where things are now. But that building that neural net, it was a PyTorch model. Building that neural net PyTorch model took us a long time, and just getting the data transformations right. Just getting the data transformations right was an extremely painful task. And it may have improved by now, but make sure that we have some heuristic for filling in nulls. Make sure that the features are all normalized and scaled appropriately. Like this feature, it has to be shifted, or we have to do a log transformation because of some argument. This feature, like it's a categorical feature, and we have a couple of different ways to treat that. And so going through that process of figuring out like what data did we actually want to feed the model, what were the things we wanted to expose to the model, was extremely painful. I mean, it was I would say months, but it was like at least a month, 2 months of figuring out exactly how to feed the data into the model in the first place. Whereas with the gradient boosted decision tree models, we were running LGBM in production there. With the gradient boosted decision tree models, it really was, do you have some crazy new feature that you want to incorporate into the model? Go find it in the data lake. You build a Spark job to build a data set and run it through and go train it today. And it was a come in the morning, and it took all day just because the Spark jobs took a long time to run. And at the end of the day, you'd leave at the end of the day and you'd be training a model. Whereas, if it's a neural net, now you have to figure out what are the transformations that I want to do on it, and you have to figure out how to feed that data into the model. Whereas the gradient boosted decision trees, they'll handle crazy distributions in your feature space. They'll handle collinearity. They'll handle collinearity messes them up a little bit, but they'll handle collinearity better than some other modeling approaches. They'll handle missing values really easily. And so to me, all of that stuff that saves you a tremendous amount of time, right? And you can try more stuff. You can do more feature engineering, right? You can try different hyperparameter tunings, like different ways to play with trees and stuff. But that frees you from like the data engineering part of the work, right? Like everywhere on LinkedIn, everyone complains that data science is 80% data engineering. Get over it. It's what it is. But with gradient boosted decision trees, you can kind of ignore a lot of that data engineering that you normally would do, especially if you just want to see if this particular data set has any sort of predictive power in it. So there's always relationships in a business that everybody knows, right? There's always relationships in the business that everybody knows. And LGBM has a lot of ways to kind of enforce those priors. If you want to think about it slightly differently, you can think about these as ways to regularize the model, right? These are ways to sort of ameliorate some bias that you may be picking up in your data set, right? So good ways to, we said early on, these models overfit pretty easily. You have lots of ways to kind of, prompt them away from the regime where they're overfitting. So these are specific to light GBM. These are three options that you'll find in either, I can't remember if it's in the constructor or the fit method, but if you search light GBM and parameters, you'll find a list of hundreds of different parameters for LGBM. And these three are three that I found particularly useful, and I wanted to call them out here. So the first one that I really like, monotone constraints. In that one, basically you're enforcing, you enforce a function, you enforce a monotonic relationship with one of the regressors, right? So example here, suppose I have, I have a news feed or something. I have a search result page. I have a recommendation algorithm or something, right? And I want to rank these products, or I want to score these products in terms of their desirableness to a particular customer. it is generally the case that some of those products you have, you earn more money from than the products that than other products, right? There's some products that have a higher margin. There's some products where a manufacturer has paid you to sell more of them. There's sometimes you get an incentive for selling something, but there is a concept of a partner brand versus a non-partner brand, right? If you want to find a non-partner brand, go to Expedia and try to find a Hilton hotel, right? That is what they call a non-partner brand, right? So we need to enforce business logic that partner brands always appear higher in the product feed than non-partner brands, right? And so this is with a monotone constraint, you can have a feature called partner brand, and you can force the model to say, my score is an increasing function of the partner brand feature, so that I guarantee when my partner brand feature is 1, the scores will be higher than when the partner brand feature is 0. You can do this after the fact as well. That's how we did a lot of things at Expedia, was you would have some initial model score and then you would kind of rearrange the results to fit some business logic. But there's lots of ways to do it. This was one of the ways that we were exploring, kind of incorporating the business constraints actually into the model and maybe getting some better optimization results as some better results as a result of like the actual optimization happening within the model as opposed to outside the model. Another one, force splits. This one is actually really interesting too. But for this one, you can actually specify in LightGBM, you can specify to the model every time you build a tree, the first split of that tree should be on the same feature. You should always split on the same feature first whenever you're building a tree. So if you do your gradient boosting algorithm and you say, I want a stack of 100 trees, the first split in each of those 100 trees is always going to be on the same feature. So you might use this, for example, if you want to treat two things like slightly differently within the same model. So for example, if I'm building a model where I'm trying to predict what is the time a customer visits my website today, and how long do I have to wait before I expect to see this customer again? Right? I'm trying to predict when the customer is going to return. We may want to treat new customers or customers who have been customers less than 30 days differently than we treat existing customers, because we know from our user research, from our conversations with the product team, new customers take 30 days to onboard, and new customers don't see the full value of the product for the first 30 days. So I may want to force a split on customer type. I may want to force a split on, has this customer been a customer less than 30 days or not? And now I can treat new customers and existing customers within the same framework, within the same model. So that's one that we've used before. The other one that I think that's really interesting too is interaction constraints. So in this case, this will actually force two features to interact, and interact in the tree models means that they split in the same branch, right? They split in the same branch. And so for these, this is really useful if you have a large feature space, right? If you have a large feature space and you don't have enough data to learn known relationships, you can give the model this information and it'll do better. So it doesn't have to, I kind of think of it as like allocate more variance, but I don't think that's quite right. You force it to interact here. So you give the model a hint and it allows it to focus on, building stuff around these constraints that you from the outside know, but otherwise the model might not be able to discover because you may not have enough data, or the feature space may be too large. Under the covers, the reason what's happening here is, if you have a very large feature space, every time you build a tree in these packages, whether you're doing bagging, building an ensemble, whether you're boosting, building a stack of trees, every time you build a tree, what you do is you sample the feature space, right? So if you have 100 features, you may choose to build a tree based on 80 of them. And you do this over and over again. You kind of resample your feature space, right? You can replace and everything, but like you resample your feature space. And so you can't always be sure that in a particular tree, you're going to have the two features you need to interact. If you force the features to interact, you'll ensure that every time one of the features shows up that will use the other feature and that you can get that interaction. And so it can, regularizing the model, giving it ways to enforce priors can help speed up the training a little bit or improve the training a lot, actually. Early in my career, this would have been my response. In my first couple of years as a data scientist, it would have been my response that, oh, well, the model should learn these relationships. If there is truly a monotonically, increasing relationship in nature, the model should learn that relationship. right? If there truly is, a dependence of price on demand, right? If demand really does depend on price, right? Then the model should be able to figure that out. And like I was typing this slide the other day, I like laughed at myself thinking that, right? Because nature is always messy. Nature is really messy. You have to deal with all kinds of crazy data sets. You get missing values. You like, oh, this production system wasn't spitting out data for 2 months and nobody noticed because the engineering team didn't have monitoring on it. And so now I only have 2.5 weeks of data and I have a timeline. There's a lot of stuff in the real world, stuff that happens in business that pull you a long way away from kind of the ideal situation. And so in those instances, there's some things that you just know. I used the demand and price example earlier. We know the demand goes down as price goes up. Like, oh, we have these couple of points in the data set where the price was really, really high and demand was ridiculous. Should the model key on those points? Like, oh no, it was the day after the Super Bowl, or it was the blah blah blah, or it was the red ones. Like for some reason, this color red was trending, and everybody wanted the red ones, and we happened to have the price high that week, and we just sold a ton of them. It's some external thing. You can communicate this information to the model, and ultimately drive better performance. Like, what does performance mean? Is it an F1 score, right? Is it a precision, accuracy, recall? Like, at the end of the day, performance is, did you make the business any more money, right? And that's really what you're going for. And so, if you get a better fit on your training data and your validation score is better with this model, but you don't actually make any more money for the business, like what did we accomplish here, right? And this is also another sort of crazy but true thing. You can have a model with worse online score, or sorry, excuse me. You can have a model with worse scores offline in the evaluations, but actually performs better online. Ranking models are a really great example here that we dealt with, because you get tons of biases in the data set. And so you can do a really good job of fitting the data set and then go test the model and you have a conversion loser, because all you did was just kind of reinforce the biases. You reinforce the biases in you reinforce some of the biases that were in the data set. So you may add some variance to your model. You may add some bias to your model to really improve real world performance. And that may affect your performance metrics at the end of the day. Now, that's a good thing, because your goal isn't to get good performance metrics. Your goal is to pay your salary and then some, right? So we say GBT is easy to understand for stakeholders. GBT wins on tabular data. It makes your life easier because you can get to show a model. You can get to a model more quickly. We just discussed about enforcing priors and lots of different ways to regularize the models to your heart's content. The last thing I want to talk about is explainability, and I think for me, explainability is it's kind of like I feel it's a little bit like fusion. It's like always, it's going to be important in a couple of years. The good news is fusion looks like it's getting closer and closer to reality. I would say explainability is one of those things that's getting closer and closer to something you not want to learn about, but something you have to learn about. I think that there's going to be stronger and stronger desire for people to understand the predictions of models, understand how the model is making a particular prediction. And I think that in a lot of cases, these are going to be enforced by governments, right? Governments will demand to know how a model is making a particular decision. What features are important when making a decision about, whether someone can be approved for a mortgage, right? Or whether you can extend credit to somebody, or whether to fire somebody, right? All of these things, like there's going to be legislation around these things, I think, in the near future about explainability. I think the time where we can publish models and not have to worry about why the model is making the decisions it's making is coming to an end. So I'm going to talk about two major concepts here for explainability. So the first one is the easy one. This is feature importances. You can get these really easily out of all of the gradient boosted decision tree packages. There's two different flavors of feature importances, and it's worth reading the documentation of the packages to really understand these, but essentially this is how it works. Two modes. So either you're looking at information gain in this chart, or you're looking at total splits. So let's talk about total splits first. It's a little easier to understand. So total splits. when you for each feature, right? The model has some crank that it turns, and it samples features. It picks out of the sea of features. It picks a feature and it chooses to split on it. There's some principled way in which it chooses which features to pick. All you have to know is that the features that it picks some features more than others, right? It picks some features to split on more often than others. And that the way that it picks those features is ultimately driving down the loss function, right? So if you look at the feature importance, if you look at this chart in terms of total splits, right, what you're looking at is the stuff at the top, the stuff with the longer bar on this chart, is the features that the model chose to split on more often, right? And so when you say, like, well, which feature is more important? Well, if the model is preferentially splitting on a particular feature, then that feature should be more important to the overall prediction, because it's always being split on. The model is always saying, hey, this thing right here, it reduces my loss function more. Okay, so that's the total splits. Which features did the model split on more often? The other flavor of feature importance that you'll get kind of along for the ride in these packages is information gain. And so information gain is it's kind of an average statement across all of the trees in your model, right? What was the average gain in information that you observed across all the trees in the model when that tree includes that feature versus when it doesn't? And that's sort of another way to get a similar information. In practice, the two charts will be very, very similar. You may have features that provide a ton of information, but that don't get split on very often. I haven't really encountered that in my career. But there's two different ways to calculate it. And the one thing to call out, though, is that neither of these approaches answers the question, how did the model make this decision? Okay, this is aggregate. This is average across all of the trees in your ensemble. This is not looking at the particular prediction. This is just looking at, how often did the trees split on this feature? How much information did this feature give when the trees chose to split on it, right? So this isn't telling you anything about any particular decision that the model has made. But it turns out you're really going to have to explain a particular decision that the model made a lot. And so that's where you have other approaches that are, I think, very, very important, very, very worth learning, very, very worth understanding. The approach that I really like, there's several different model explainability approaches. But for me, Shap values is the best way that I found for me intuitively to sort of understand what's going on in the model. Excuse me. So a slide aside here, Lloyd Shapley, go look him up on Wikipedia, pretty interesting guy. He was a game theorist in the 50s. He was concerned about, how do I divide up the winnings from a multiplayer game? Okay, so what's the situation? What's the analogy? You go to play soccer, right? You go play football. I don't know soccer. I'm American, so I'll say soccer. You go to play soccer, and the winner of the soccer match gets $1 million. The team that wins gets $1 million. So you go to the soccer match and you have one guy on the team who scores, there are one woman on the team who scores 30 goals, right? The goalie, can lay down and take a nap. The person who scored 30 goals had the ball the whole game. There was no defense necessary. There was no passing. There was no blocking. There was one person just, completely dominating the other team. All right, hey, surprise, the team that scored 30 goals wins $1 million. How do you divide that $1 million up? Is it fair for everyone to get the same amount of money when the goalie's taking a nap and one person is scoring 30 goals? We generally say, yeah, we should divide it evenly, but that's technically, it's not fair. The person who did the most work, the person who scored the most goals, should get most of the $1 million. And this is the question that Shapley wanted to understand, is like, when there's a game between several people, how do I divide the winnings of that game in a fair way that respected the contributions of each of the players in the game? So 2017, Lundberg is I think he's a UC Irvine, I believe, or UC Riverside. But he wrote a paper, and I think with one of his collaborators, where he adapted these ideas to machine learning models, right? So instead of how to divide up the payout among multiple players of a game, we want to understand, how do I explain a prediction in terms of the contributions of each of the features in the feature space? So this is 2017. It's a great paper. It's not too mathy, definitely worth reading. At the end of the day, you get like, this is a great approach in principle, but calculationally, it's extremely intense. And so like in principle, it's a really good idea, but at the end of the day, what you're really doing is estimating. And, again, like you have you have the same sort of question. So, but in 2018, Lundberg and his collaborators showed that for tree models, you actually get some calculational efficiencies, and you get additional benefits specifically in the case of trees. The technical reason why, and I should have read this paper again before I talk about it, but what I remember is that you can actually look at the trees and you can understand how features are interacting in the trees. And that gives you some additional calculational efficiencies that you can leverage when you're calculating these SHAP values. I think the challenge in calculating the SHAP values in the first place is that it's like an NP hard problem, but because the trees, the architecture of the tree models, you can see specifically how the features interact. I think you can cut out a lot of the calculations that you would have to do otherwise. I think that's the point of that paper, but please don't quote me on that. So the main point, SHAP values help you understand how a model is, how to divide up a particular prediction in terms of each of the individual features. And you get benefits from them specifically in the case of trees, so that the answers that you get out of SHAP are more trustworthy than in tree models than in some of the other modeling approaches you can use. So those papers are fantastic. Go and look them up and read them. Just as fantastic as those papers is the GitHub repo that Lundberg published. So you can type SHAP Lundberg or GitHub SHAP, and you should find his GitHub repo pretty easily. This is just cut and paste from this repo, and I will walk through this example so you can sort of see how simple it is to produce these, and then how they kind of work to explain predictions. So this is the Boston housing data set. If you're not familiar with it, we want to predict the value of a home based on several dimensions. It's a regression problem. There's a great write-up on it in Kaggle. If you don't know this data set, go play around with it because it's a common one. Okay, so what are we doing here? We just read in the data set and we just fit some simple regression model to it. We're not going to do any engineering or anything fancy with it. Then we run the model through the SHAP explainer. And so we use the model to build the explainer. So that's what's happening in the third line there. Fourth line, we get the SHAP values from the explainer using the original data. All right, so SHAP values, this is going to be a matrix. Each data point is going to be explained by a locally linear model, and we'll talk about that in just a second. And then, so this line is this, then we're just going to plot it. All right, so what are we doing? We're plotting SHAP value 0. So this is the first data point in that data set. And we're looking at what did the SHAP model predict for that? And what were the things that drove the value up and drove the value down? Okay. A lot of words there, so let's talk to it a little bit more. At the end of the day, the SHAP model is a linear model. It has a constant term associated with it, and I apologize for the text size, but for this particular data point, the constant term is 22.5, and you can see that down at the bottom. That's the expectation value, so you take out the average. The predicted value that you can see at the top right here is 24.0. So that's the predicted value. And the question is, how did you get from 22.5 to 24.0, right? There's some features whose contribution push that value up, and there's some features that push that value down, right? So the RM feature, for example, had a very large negative contribution to the overall prediction. But the LSTAT feature had a very, very large positive contribution to the overall prediction. Okay, we're predicting the value of a house, right, in thousands of dollars. And what we find is that in this case, for this instance, the value of LSTAT that we observed really pushed the value of the house up, whereas the value of RM really pushed the value of the house down. And this is how you can explain a single prediction in terms of the SHAP value. So why is this house valued the way it is? The model predicts $24,000 home value. And I would be willing to bet that nobody's paid $24,000 for a house in Boston in a very long time. But you get a $24,000 home value. What went into that $24,000? Why is it $24,000? The average in the data set is $22,000. And the reason that this one is higher is largely due to this feature LSTAT. And so this gives you a way to have a conversation about the predictions that you're making. This gives you a way to have a conversation about the predictions you're making in terms of the features that you're using. And this is every one of your stakeholders will beg you for a conversation like this when you're walking through a model. Again, there's lots of different plots in the SHAP library. I would, again, encourage you to go through and play with it. Build some simple tree models, run them through the Shapley analysis, and take a look at them. This is a very interesting relationship between two features, RM and RAD. And so what is this? What are we looking at here? So each dot on this graph is a different data point, right? It's a different one of the data points in the data set, right? You had the X's and the Y's. Each one is a row in the X matrix, right? And you can see that, sorry about that. You can see that you have this really interesting sort of linear-ish relationship when RM is bigger than about 6.5. So at about 6.5, you get this really strong positive linear relationship between RM and the SHAP value for RM, right? The SHAP value for RM is the home value that you're trying to predict, right? It's the thing that you're trying to regress on. And you see that you see in RM, you have the SHAP values become positive very, very quickly as the value of RM goes past 6.5, right? And so you get a very strong positive contribution for large values of RM. But there's also another interesting interaction with this feature, RAD. You can see up here in this cluster of points, right in this top right corner here, all of them are blue. So they have very, very high values of RM and very, very low values of RAD. And that contributes to a very high impact on the overall thing you're trying to regress, in this case, the house values. So relationships like this, if you can, using the SHAP analysis, you can find relationships like this. And this allows you to understand how this feature interacts with the overall prediction. It's very, very interesting. At Verbo, it's a story. At Verbo, I ran our ranking model through the SHAP analysis once it was after 2018, and they became tractable after this 2018 paper. So I ran our ranking model through this, and I found a very interesting relationship between the ranking score and star rating. And it's completely intuitive. You guys know it, or y'all know it yourselves. What we found was that below some value, and it's like 4.7 or 4.8, star score did not matter. But from 4.7 to 5, you had a very strong positive relationship like this, right? So if your home on Verbo was below 4.7, it didn't matter. It just doesn't matter. But once you got to 4.7, there was a huge incentive for you as a homeowner to get from 4.7 to 4.8. There was a huge incentive for you as a homeowner to get from 4.8 to 4.9. How do y'all shop on Grubhub? How do y'all shop on DoorDash, right? How do y'all shop on these online marketplaces? You look at the star rating and you say like, 4.5, I don't know, it's lunch. Like this place is fine. Or if you're going, you want to order dinner, you're like, 4.7, I don't know, this place is 4.9 and it has 300 reviews. So maybe we go with the 4.9. There's a huge effect of like just a very small change in star rating. And that was sort of this Shapley analysis is what revealed that for us. And it was something we intuitively knew, but we couldn't quantitatively show until we did this analysis. The last, there's a few other plots, but the last one that I want to call out here for in the SHAP value, this looks very similar to the feature importance plots that we showed a few slides ago, and I think intentionally so, but it gives a lot more information. So remember when we were looking at the feature importance plots that like GBM or XGBoost gave you, it told you generally how the model worked. It didn't say anything about a particular data point. In this plot, each point is a data point. Each point is a data point. And the value of that feature is encoded in the color, right? So how do we read this? The first line is LSTAT, which we saw before. What we see for LSTAT, when the value of LSTAT is high, so when the value of LSTAT is red, when the feature value is high itself, it has a very large negative SHAP contribution. But when the value of LSTAT is low, when it's blue, it tends to have a positive or strongly positive SHAP contribution. So this is saying that like my LSTAT, if I have a very low LSTAT, it's going to drag the value of my home down. If I have a very, very low value of LSTAT, it's going to push the value of my home value up, right? And you can look at all these features and you kind of see some really interesting things pop out. The other thing that this plot tells you is it tells you something about the distribution of this feature. So again, if we look at LSTAT or if we look at DIS, DIS has a pretty interesting distribution. The width in the Y dimension, the width of this shows you how densely the data points are packed. So you can see there's a huge density of DIS that has a moderate feature value. So you see some blue and some red here, so a little purple. You have a very dense packing of this DIS that has a very, very small impact on overall SHAP value. Likely for LSTAT, you have this region out here a little bit to the right. This stuff has a really interesting distribution. You have a buildup of data points right here for LSTAT, and these guys tend to have a positive contribution to the overall SHAP value. So this gives you sort of some concept of feature importance that is similar to, in some respects, the feature importances that I showed earlier. But it's a little bit more rich because this is actually looking at individual data points and how individual data points impact the high-level prediction. So in the talk a little bit here, and I will apologize in advance. This is a bit of a soapbox for me. Like, if you want to call yourself a scientist, like, you should be curious, right? If you want to call yourself a scientist, you should look for explaining and understanding the way that things are, right? That's what scientists do, right? Scientists look at the universe and they try to break it down into really simple building blocks. And they try to understand how things interact. They try to understand why things interact. And they try to understand, to the extent to the extent that those things interact. And when they understand those building blocks, then they build them on top of each other. They build that intuition. On top of that intuition, they build deeper and deeper understanding so that you can start to model. If you really understand the fundamental building blocks of the problem, you start to build up an understanding, a complete understanding of the problem. You can build more and more complex models. You can build more and more, you can infer more and more things about the situation about the thing you're trying to model, as you build a deeper and deeper understanding. And this is what science is. If you're a data scientist and you don't care about model explainability, it's like you're kind of more of a software engineer who knows math, and I think that's a distinction that a lot of people in the field don't really make, is that there's, if you're really, really good at throwing together neural nets and throwing them at problems, that's awesome. But like, that's an engineering job. That's not necessarily a data science job, I think, in my opinion. Like, really what a scientist is understanding how those things are interacting and using that understanding to build a model on top of it. And to me, like, the Shapley analysis, the gradient boosted decision and the pairing with the gradient boosted decision trees is a tool for you to build pretty good models that we've shown, but also explore the feature space you're looking at to really understand the nature that you're trying to model. And so I would encourage all of y'all to stay curious about that stuff. Really stay curious about the things that you're trying to model. The upside to this is that correlations are really, really interesting to the business. Interesting correlations, correlations that were unexpected. Those are things that the business can action. Like, okay, hey, Ben, correlation is not causation. Like, I get it, but you can always run an A/B test, right? If you can give the business 10 things that are correlated and you can run some A/B tests, probably 2 of those are causal. And those are things that you can actually trade on. Those are things that you can help improve, customer conversion. You can help include operations for the business. Those are things that you can actually test and learn and contribute to the business. But you won't get any of that if you don't really understand what your model's doing, how your model's making decisions. I've talked too much. Like I told y'all, I'm a talker. Go try this today. Light GBM. The examples I've used here were Light GBM. You also saw XGBoost. You can pip install Light GBM. You can Conda install Light GBM. I don't know about Cat Boost. I've never played with it. Light GBM is all 3 of these run in production. I told y'all Expedia, we used Light GBM to run our ranking models on Verbo.com. 10 million searches a day, $8 billion in commerce through those ranking models. XGBoost, I know, was also running at Verbo in several places in production. CatBoost runs in production, I believe, at Yandex, which is the Russian equivalent of Google. These are all free open source packages. They have fantastic open source communities. Go and look at the GitHub questions in LGBM, and you find, the guy who originally wrote LightGBM, what I get 10 years ago, maybe 5, 6 years ago. He's still there, engaged in answering questions. So fantastic communities, lots of resources to understand how these models work at a high level and at a quantitative level. So I would encourage all of y'all to go and try playing around with these models. Today. Are there any other questions that I can answer?
Yeah, I mean, great. First off, thanks a lot, Ben. I think it was super resourceful, and I mean, even I learned a lot of things on sidelines, and it's fun interacting. I mean, it's fun to learn from your experiences, especially when you applied it at scale. So with that, I mean, I'll probably ask a few questions. I think there are a few basic ones, and there are some curious questions as well. So I think someone is asking, does data engineering come first after data science? I mean, do data engineering comes after data science? This was the question.
It can. It doesn't have to. I think for these models, one of the things that's great about it, and I would like to call this out a little bit more strongly, is time to value, right? Typically, as a data scientist in an organization, Jiffy is a small organization. We have a small team, so a lot of the data that we have is all in the same database, and we can get new data feeds, we can engineer some new features and stuff, but it's all kind of in the database already. And the value of these gradient boosted tree models is that you can just, run a query against a database and send that data directly into the model. So there's some data engineering involved in getting that model into the database in the first place. But, the amount of data engineering that we did there was very, very minimal, right? What I mentioned before, in experience at Verbo and Expedia, data engineering can take as long as you want it to. It's a whole different organization. Yeah. So if I wanted a new feature and I wanted to go through the data engineering team, I would write a Jira ticket and build a business case, and then go talk to some director, and then maybe have to, beg some senior manager to prioritize, and then follow up on it with the project manager and the team. And you can go through that process if you want to. And we did often, but sometimes you just want to build a model to see if it's even worth getting the data in the first place. And in that case, the gradient boosted decision trees, hey, we got this new feature. Is it worth going through the full data, the data engineering crank, and turning everything and cleaning the nulls and making sure the monitoring on this and making sure this and building our production feature cache and feature store this? And is it worth all that? Well, let's just pull it, throw it into a CSV, and throw out the trees and see what the trees do. Do the trees find any predictive power with zero processing on this? Yes. Okay, well, that's awesome. We should prioritize this feature because we know that if we clean it up and we work real hard on it, it's going to give us more value. And so it's a what I would say is that as a data scientist, if the extent to which you can decouple yourself from that process, the extent to which you can do it yourself, the extent to which you can choose models that obviate some of those problems, that's going to determine a lot of your success early in your career. Early in your career, it's about doing it more. And if you want to get good at data engineering, spend all your time building Spark jobs, because you'll never not have a Spark job to build, right? Spend all your time feature engineering for someone else, because you'll never not have that job. If you want to get good at modeling, then spend more time with models that allow you to do more modeling. And that, to me, that's the value of really simple approaches like this.
Got it. Totally aligned on that. And there is a question from Alan. Just curious, how does it go with regulations when we try to bias model training? I think somewhere in the slide, you mentioned on this. So I mean, maybe your thoughts on it. Yeah.
So I'm a little unfamiliar with regulations in terms of government regulations, or usually you have to bias, or you have to add some variance to the model to get rid of some bias in your data set. You can do the other thing. You may have a high variance data set that you have to bias somehow. Like the example I gave was, maybe you have a large feature space and you don't have enough data to discover some relationship. So you bias it, and you give it some bias, and so that you tell it about that relationship, in terms of I guess I'm a little bit confused from the regulation point of view. Is that the regulations don't necessarily care about the training; they care about the decisions that the model is making. If I'm thinking about, like zip code, right? Zip code is a loaded one. There was a whole thing 5 years ago or 10 years ago about, using zip code to determine whether someone is eligible for credit. Because, hey, you can look and you can see in certain zip codes, people don't pay back. They don't pay back their credit cards with as high a frequency as other zip codes. And so we use that in our model. But why would that be the case? Well, you have a bunch of poor people in one area. And so now what you're doing is you're training your model in a way that kind of says, like, okay, all of you poor people are not eligible for credit because all you poor people are poor and do a bad job of paying back your credit score. Like, there's racial issues there. And so there's ways that the government has to step in and do that. I think, like, actually biasing the model somehow or adding some variance to it, that's actually how you will get rid of some of those issues.
Yeah, thanks for that. And I think this was asked before you started explaining about SHAP. But the question is, may I know what are some of the best practices followed in real world production to explain black box models? And
So we
are
use,
live SHAP robust enough?
we use SHAP. Yeah, we use SHAP at Verbo. And so all of them are, so there's, and I would encourage y'all to go and read this. It's a fantastic distinction to understand, is the difference between interpretability and explainability. So SHAP, Lime, Eli 5, there's a couple other ones. Those are explanations, right? So you're building a model locally, hopefully near a decision boundary or not too far away from a decision boundary, where you can, and you sort of focus on the fact that, in a small enough neighborhood around the point, things are basically linear. And so that's an explanation that it's a locally interpretable explanation. It doesn't sort of apply globally. Lundberg and his collaborators have some paper in I think it's actually 2020 that I haven't read, but it is how to sort of go from like a local explanation to a global explanation. So that's a technical thing that I don't fully understand that one yet, but those are explanations. There are interpretations as well. You can see, for example, customers like you also bought, right? Other popular products include, right? Those are sort of more global interpretability things that you can build neural architectures to get those interpretations out. For example, going in, if you feed a knowledge graph into your neural net, you can go and look at, like, hey, like, what are all the things that are connected in the knowledge graphs? Like, clearly that has to have an impact. So so I think that all of these processes are including improving. I had, like I said, it took me an hour to update my Conda environment last night. There was a new a version of the SHAP repo. So yeah, all of these things are improving, but yeah, they absolutely do run at scale. They are, they are robust, especially in most of the regimes that you're working in. If you're far from a decision boundary, if your parameter space is sharply peaked and the linear assumption doesn't apply, then they're going to give some challenges there. But that's, those are sort of limited cases. And I would not, especially if I had a tree model, like SHAP would be the first thing that I tried to understand. And that gives you some intuition about some things.
Got it. Yeah, thanks for that. And I think before we wrap up, I have a final question.
Yeah.
I think, it'll be great to know your journey to data science and how you got started with it, and what would be your piece of advice to the learners. Yeah,
absolutely. Yeah. So again, I started data science kind of in the Wild West days of data science. I was a software engineer. I worked for a company valuing credit derivatives. I got in 2010, 2012. I got laid off and I was in Vancouver, British Columbia, and came back to Austin, Texas. And a little bit of an existential crisis. Like, I don't know what I want to do. I don't know what I'm good at. And so I thought for a long time, what is it? If I can do anything, what can I do? And I wrote like a paragraph, a mission statement, a paragraph. And it was like, I want to build models. I want to understand how things work. I want to put math to them. And then I want to use that math to kind of predict how things will behave. And I didn't know the term data scientist. I didn't know, I found like, I probably need to know SQL. So I picked up, a few books on SQL and started kind of teaching myself. But really, I took that paragraph and I stapled it to my resume and I just sent it to every email address at a startup I could find in Austin. And I was very fortunate. It was like right place, right time. 2012 in Austin, there weren't a ton of people who had kind of the background and qualifications or the desire to do the stuff that I was interested in. So, I started at one startup. I went to another startup. I dabbled in product management for a little while. I was a terrible product manager, but it really, really helped my career in terms of understanding how to talk to the business. Like, what does the business want out of data science? What does the business want out of analytics? So I would say, number one, like I said at the beginning, take all of my advice with a grain of salt, because I'm from a different time, like a different generation of data science, and getting into data science, for me, it was like, hey, I'm a data scientist and give me a job. And I know that it's not like that today anymore. But I will say the thing that has really, I would say, there's a couple things I would say that, as professionals, for y'all to consider. Number one is, and I've said this, I think maybe 2 or 3 times, stay curious. You've got to be curious. You have to be curious about what you're doing, why you're doing it, why it's important. Stay curious about that. Don't be intimidated by math. Math is just another language. Don't be intimidated by it. You can learn it. Everybody can learn it. Don't be intimidated by the math. And I told you, like, I don't consider myself great at math, but I have a PhD in theoretical physics. Like, you can do it, you can figure it out. You just have to bang your head against it. And number 3 is, and this is kind of a more general career advice. I think this applies to everyone, not just in analytics, but I think lots of people need to hear this, is that at the end of the day, you could be really, really smart and really, really hard to work with, and that's going to cap your career. I worked with what I think was like one of the best software engineers I've ever known, probably the best software engineer I've ever known. The guy, he would walk, between meeting rooms, and the other software engineers would like throw rose petals at his feet, right? Incredibly good software engineer, but impossible to work with, right? Impossible to work with, impossible to sort of get across. I was a product manager. He was the lead developer on the team, and I couldn't get across to him. We have to do this because we will make more money if it works. And if we don't do this, we will not make that money. And it was, having that conversation about, like, here's the business objective, and, trying to get to a good place. And it was just hard. And so I'd say, like, you can be really, really smart, really, really hard to work with. And I would say I would much rather have someone who was slightly above average, but very, very collaborative. Someone who was, a good data scientist and not necessarily a great one, but who came to work every day with a positive intent. Someone who came to work and said, I want to help today, and let me know how I can help. What can I do to help make all of this that we're trying to do better? At the end of the day, having a job is kind of like working on a group project, right? But you get paid and you can get fired from it, right? It's just like high school or college, where you have these big group projects. And at the end of the day, the group projects that do the best, the group projects that get the best score and have the best showing, those are the ones where everyone comes to the project and says, what is it that we all are trying to accomplish? And where does my role in that? How can I contribute to what it is that we are all trying to accomplish? Early in my career, I came to the group project and said, oh, well, I'm going to be the one who gets the A. Whatever y'all do is fine, but I'm going to get an A, right? What is in this job for my career, right? That's how I started my approaching things. But when I took a step back from that, and when I tried to say, how can I help us accomplish what we're all trying to accomplish, and we all can win at it, I would say that my career just completely changed overnight. So come to work, show up, have positive intent, figure out how you can help, what it is that you are uniquely good at and that you're uniquely great at. How can you leverage that to help what other people are trying to accomplish? And I think that, to me, it almost doesn't matter how good you are at math. It doesn't matter how good you are at Python or, anything else. If you just really, truly want to help and you have that deep desire, like, those are the types of people that I want on any team, data science or otherwise. I would also encourage y'all, please reach out to me on LinkedIn. If there's any questions I didn't answer here, if you're confused by something, reach out to me on LinkedIn. My schedule is kind of spotty and sometimes hectic, but if you want to have a quick one-on-one, happy to sit down and chat with people face-to-face, but please reach out to me on LinkedIn.
Thanks a ton, Ben, for extending that support, and also thanks a ton for walking us through your journey. I think everyone looks at the final finished product. I mean, okay, Ben is VP and head of data science, but I think there is a lot more that goes into making what you are today. Thanks a ton for walking us through the struggles and to achieving what you are today. I'm sure a lot of us and a lot of them in the community are also facing through some struggles, but I think it's the hard work, it's
Yeah.
pain that walks
Yeah.
them through the journey and makes them
That's right.
what they wish. Yeah.
The only person who can keep you down is you. It's true. It's just true. It's just true. So awesome. I really appreciate the opportunity.
Yeah, thanks a ton, and have a great rest of the evening. And thanks a ton to everyone for joining us. And thank you. And we'll come back with another live session very soon. Take care. Bye.